Thank you. It's great to be here with all of you. Some great talks this morning. As a vendor, obviously seeing, well, I think everyone here is a customer of Intel at one point or currently. So it's great to kind of hear what's going on in the field. It's very informative for me, and I appreciate it. So I'm going to go through and tell you about some pretty significant changes that are coming to the toolchain for the Diamond Rapids project. That's the internal name. It's been disclosed. The official public name will be coming out here probably towards the end of the year. I really want to give credit towards my colleague, Victor Rodriguez. If any of you have been to any Linux conferences in the past, he's usually the one doing the compiler updates for Linux. And to his credit, a lot of this work I'm showing you here today comes from. So 3 big changes we'll go through, and I'll show you examples what we have. So we have an update to a vector type AVX10. So this one's pretty significant in that it kind of removes a lot of the need to understand, okay, what's the underlying hardware? Does it support 256 or 512? So now you're getting to something that's very agnostic, and it can determine what you have to do at runtime versus compile time. APX for scalar extension, so probably the biggest scalar update Intel has made since it introduced 64 bits, probably 12 to 14 years ago. And then some additional new data types for AMX that I think have some pretty neat impacts for the HPC. So the one thing I'm trying to do here today ultimately for you is say, okay, here are the updates, obviously from a vendor. So how do I prove to all of you that we've done our homework and these are things that you can trust, and when you run them 1,000 times, you can get the same result 1,000 times. So that's really what I'm trying to prove here to you, to show you that, hey, you know what, Intel's done their work on this, and when you go out there and start using it, you can trust this. So we're going to go through, I'll give you examples, we'll show source, we'll show you what tools we use. A lot of this is done through a simulator called SDE. I provide links where you can go and download that. The updates here, and all the examples I'm using is GCC 15. ICC is supported, Clang as well. So you find Intel, when we do our work, right, we push them up to all the major compilers here. So I'm purely just using GCC. I had to pick one. So that's the one I picked here. And then we'll go through and give you show you the covered metrics and stats and so forth. Just say, okay, yeah, these aren't just some empty, compiler code. Yeah, the compiler really is doing its work as intended on the real hardware, or simulator hardware, I should say. Okay, so we, as I said, a lot of this is coming in GCC 15. It's a significant update. I'll do my best to kind of cover them all here. It's pretty neat. You can see the compiler flags that are available here. So the big thing that's changed here, so we have APX aware register allocation. So again, a major change in how the scalar functionality works in x86, along with mask first vectorization and mixed precision lowering. All this, I think, you'll go through and hopefully see from the examples I give of why it matters, and it's going to help out your performance. And the nice thing about the compiler ones, right, that's your easy button. Those are the things you enable these flags. You kind of get that for free. And I always recommend, whenever you want to do any optimizations, use the latest compiler flags. There's a lot of effort spent at Intel to make sure that those are performant. And then at that point, you can do the deeper analysis and understand, okay, where else do I need to go fix and optimize to make my code work faster? So just highlighting these, and I'll talk about these a lot more in the talk. So big thing on APX, we've doubled the number of general purpose registers that are available. So from 16 to 17, you'll see some nice performance improvements there in terms of being able to stay in the registers there along, be able to scale up into them versus having to hit memory and so forth and get the penalties for that. We add FP8 and TF32 tiles support in AMX. So again, for a lot of the adding these additional data types do some pretty impressive things, what you'll see here. From the HPC standpoint, we're talking about dot products or matrix multiplication, right, doing tiles. And then the other big thing I mentioned is in the AVX 512, we're moving to a vector length agnostic model. So one of the challenges we kind of heard from customers is saying, okay, you got these E cores, the efficient cores, or AVX2. No, you have AVX 512. It's been supported since Sci-Fi Rapids, around 2020 or so. And you have to know the CPU ID and specifically a compile time. Pick the right one there. It makes portability, not very portable, quite frankly. So from this here, this kind of hopefully goes away. It's only forward compatible. Unfortunately, nothing we can do on the current ones now, but starting with Diamond Rapids and going forward there, at least solving that problem. All right, enough about that. Let's get into some cool stuff. We'll start with APX. So APX, as I said, yeah, major new update from Intel. So it doubles the number of general purpose registers, as I said. Also it adds removing false dependencies, 3 operand integration is available, several other things here as well. So, but what does it all basically mean? What it basically means is that you'll see about 10% fewer loads and about 20% fewer stores in your applications. So databases should benefit, data analytics should benefit. You'll see things in the Linux kernel performance will benefit. Load stores are, if you look at instruction count, right, load stores still make predominant most of the things the CPU does here. So we went after one of the traditional heaviest usage and bottlenecks in where the applications spend a lot of their time. So a summary of where we are here. So again, I won't go through a lot of this here. So again, the big thing is you now have additional registers from 16 all the way up to 31 here. So again, when you have a lot of things that are, specifically on this one, it's about reducing spills in register pressure heavy kernels, right? So a lot of things that I heard here today that people here are doing should benefit from this. And one of the ones I heard recently, hey, let's talk about sparse matrix vector multiply like kernel. So real simple little code snippet, a little microkernel here. I think all of you are far more familiar with this one than I am in terms of what its uses are in your applications. But the big thing is that it's notoriously memory bound and with a lot of irregular kind of memory access for it. So we thought pretty good application here to kind of take a look at and see how does APX do with something like this. So the slides will be available anywhere. You can look at the QR code. It will take you right to the GitHub. You can see this example and the other ones here I'm showing here as well, but not spending too much more time on this one to try to get through everything. So saying, all right. So in here, we're using Compiler Explorer on the left to kind of show you the assembly code. So as I said, everything here you can do, use the Intel SDE tool. It's an instruction level emulator. From that, you can then support Compiler Explorer here and essentially kind of see it. So the big thing here you're seeing is that now, hey, okay, with the sparse matrix multiply here, it is allocating into the higher register range. So you see in the blue there, register 17 is getting hit. So again, you're reducing the spills and improving the instruction level parallelism, especially in tight inner loops like what we have here. And again, you have 15 additional ones on top of this also. So this, I think, came from a lot of discussion, feedback we got from customers saying, the registers just too few here at all, right? It's a big, area hit to add registers onto your CPUs here. So doubling it was a pretty significant undertaking for Intel in terms of space, but certainly I think we see the benefit from what we're hearing on this, and hopefully you will see that as well when you start using it. Let's move along here. Okay, one down, 2 more to go. So AVX 10. So let's now moving along from scalars, we're going to go over to the vector side of the world. So the big thing of AVX 512 has been around for several generations of Xeons here. Couple of years ago with the E-Core line, we had support for those at 256, so you basically have two versions of Xeons, the regular one, Performance P, they're up to 512, and the E-Core, they're 256. So caused some issues with customers that just have code and they want to run them on both for various reasons that they do there. So one of the big things to undertake in there is saying, okay, well, how do we kind of essentially address this? Well, that's where AVX10 comes into here specifically. So with AVX10, you still get a 512-bit ZMM register with a basket and all the EVX encoding. So everything you have in existing AVX 512, you don't lose it. Intel is really big on ensuring that you have, continuous support on, especially anything in the ISA perspective. But now with the AVX 512, which again is done at the runtime versus compile time, you have the ability to scale up from 128 to 512. So you can pick the vector length that's best for you, and it'll just work. So again, just want to emphasize, there's no backwards compatibility, so you won't see this supported on, say, a Xeon 6 lines like the Granite Rapids or Sapphire Rapids. All right, let's look at an example here. Okay, a double precision, A times X plus Y. So kind of standard linear algebra type of math here. Simple, ubiquitous, and just show something that's a very clean use of vectorization and FMA type behavior. So we picked this one here to show a nice sanity check for what AVX10 code generation will look like. And let's take a look at that. So again, code compiler, ran through SDE, run this through code compiler. So if we go over to the right, the highlighted level on purple there, yeah, hey, you'll see the ZMM word 512-bit registers generated, right? So again, this is actual, the assembler is, code is being generated from the compiler itself. It's not just, just something like a placeholder, right? Everything I'm showing you is already available in the upstream, and with the simulators, you can start having your hand at trying it out, see how it works here already. So from this here, the scale is getting broadcast across the entire ZMM register. The loop processes 64 bytes per iteration using vector FMA. And then, you're doing the math out, corresponds to 8 double precision operations per iteration. So for the full 512 bits here. Talked about this. The main difference here, again, same capability, 512 and AVX10. Differences with 512, right? It's the vector bitness is picked at runtime, at compile time, sorry, whereas AVX 510 does it at runtime. Okay, jumping along, we're off to AMX. So AMX has also been around here. It's this third generation coming out in Diamond Rapids. It came out in Sapphire Rapids around 2020. Big thing here, we've added support for FP8 and TF32. So again, with AI evolving so quickly, these are kind of the newer, hotter data types that we're seeing from a lot of customers. And of course, with the AMX, right, we're now talking about it's matrix or tile multiplication versus vectors. So, Intel has a dedicated matrix multiplication engine in here, so you're getting a hardware accelerator, right? This isn't just, the vector engine just doing some, data swaps in between or anything else that compiler, right? It's a real matrix multiplication engine built into our cores here. So you're going to get some good benefits from it. It's worthwhile. Let's compare now between, the vector path and the matrix path. So, as you'd expect here, you do have the, on the AVX side, right, you are using all the vector operations, whereas when you get down to the AMX side, right, now you're seeing the matrix dot products, right? included here as well. So the big thing is that, if you have something that's really going to benefit from, the dot product, the intense kind of matrix mathematics, AMX is going to be what you want to go with. And I'll show you the benefit here in an example of why to pick that, say, versus AVX. All right. So in this case, we're going to do an example I'll show you here of code running both AVX 512 and AMX. So in this case, what we're doing here is just a BF16 gem workload. So C equals C plus A times B. So one's going to be done with AVX, the other one AMX. And we're just going to repeat it here many times just to stress the compute units out here and be able to see what's going on. So again, don't take my word on it that the compiler is actually doing what it is here. Here's proof for yourself again in the sample code. So here on the AMX side, you'll see the highlighted part there. Yeah, you know what? We are using the dot matrix multiplication instruction here, as you can see in the assembler code. So confirms the compiler is actually enabling the AMX flags. And this isn't just, again, just some little hand-waving little trick here. So looking at the results, and I think this is pretty interesting. So what you see, if you do, one of the other things out of the SDE tool is you can get instruction histograms out of them. So instruction histograms are really valuable in trying to get an initial view of, one, hey, is your application actually using, the correct libraries and operating correctly? It's oftentimes in my team, when we're looking at analyzing workloads, it's our first step to kind of, our sniff test to see, yeah, is it doing what we expect? And after that, you can go and say, okay, is it performing up to where we expect? So in this one, looking at the instruction histogram that comes out of the SDE tool, yeah, we can see about a 6x reduction in instructions between AVX 512 and AMX. So again, this is a very matrix-like operation we're doing, and you're seeing far fewer instructions. So the AMX engine is able to do essentially all of it in a much more efficient way, leaving a lot more cycles for other stuff for your CPU to do. Looking at the memory side, it's interesting. So you're getting a lot less memory pressure here as well on AMX. So again, you're getting going from about 16 million memory read-write instructions on AVX, did about half of that on reads rather to half of that on the AMX side. The one difference is that you do see more store pressure on AMX there, right? So it goes from about 50,000 to about 500,000. So okay, 10x seems big in the absolute, but relatively speaking, in terms of the total memory rewrites, right, it's still significantly less. So even with the higher store impact on AMX, right, you should get significant benefits from this one here as well. So again, quick summary, pretty much just reiterating what we kind of talked about here as well. So again, much fewer instructions. You can have a lot more cycles to do other things that you want on the CPU there. Benefits on memory overall. Little impact on storage, but again, net significantly less memory operations here. So less pressure on that one. And ultimately, these together, should say, yeah, you're going to see a nice boost on AMX when you're using matrix, doing a lot of matrix multiply versus standard kind of vector type of operations. I just took, just a smattering of papers available. So again, AVX 512 and AMX have been around a lot. A lot of work and research has been done on here. I've seen a lot come out of the HPC space. And just a small little sample if you want to go read more, but you do any kind of, Google Scholar or any other search out there, you'll find a ton of stuff out there. All of these have been discussed quite a bit. All right, so conclusions. So again, we talked about a lot of big changes came from here, and a lot of these came out of what we heard out of the HPC space, right? So Intel's been in the HPC space for decades, and Intel views the HPC space similar to what is say F1 or NASCAR in the automotive space, right? HPC is where everybody's pushing the boundaries, where a lot of the innovation comes out of that then becomes ubiquitous in your everyday laptops and what you kind of see every day. So, it's a big focus area for us. It will be in the future here. The other thing I want to say, Intel, despite what you may have heard, our demise has been greatly over-exaggerated. The company is doing great. It still continues to put in all the work, all the things that you trust us for. In the past, we're still working diligently, making sure that, when you get something from us, it's going to work. And, we've got the proof here to make you feel comfortable about moving over to it. And again, everything here I'm showing you, you can start exploring here today. We do have other simulators. So I work in a simulator group. So we have other simulators, a little more interesting there. We do work with some customers also. So if there's interest, any of you kind of exploring some of them more deeply, feel free to reach out to me. I'm active on LinkedIn, or you can find me in the hallway here whenever you'd like. So with that, I think I have about 3 minutes for questions from anyone.
So first of all, thank you very much for the presentation. I noticed on the slide about kind of the DAXB code with the multi-length vectors, it looked like the assembly still had the vector length hard-coded in terms of like loop counts. What's kind of the support for that in the architecture?
Again, it was just, I think, there was a little microkernel in there. I don't think there's, I think from the architecture standpoint, you're basically limited by whatever memory is available on your particular machine there, or page tables and stuff like that. So I don't think there's, a hard limit that we've kind of put in there, other than.
No, what I meant is like, the vector width could be 256 or 512, but the loop seemed to still be hard coded to like jump for a specific vector width. It wasn't dynamic.
Yeah. Okay, you're right. Very observed. Yeah, so we were just doing it in double precision. So it basically was iterating through 64 bits 8 times. So kind of like, getting to 512 that way. So I think that's what you were seeing there. I can quickly.
Right. How do you tell from the assembly? Maybe this is getting too into the weeds, but we can talk after.
So So it really is from the double. Sorry. I'm knocking everything over. So basically, it's what we're doing is the double precision words. So those are 64 bytes, and I think it's iterating over them in loops of 8 there. So I think that's how you get into 512. I could have picked a better case there to show the full 512 bitness to it there, but. Yeah.
Okay. Thanks.
All right.
Okay, so I looked at this, and I don't know what the -n up there is, but I tried this just now out. I got Y registers, and it looks exactly the same as when I use Skylake AVX 512 as the instruction thingies. So what is the special thing about the Z thing there, and what is that supposed to do over the previous AVX 512?
So hopefully you had the MAVX 10.2 flag there set.
I added that, yeah.
Okay, actually, so what it does over AVX 512, all it does is that basically, whereas we have an E-core architecture that's just AVX2 currently, and it's going to stay there, and then you have the traditional P-core architecture, so your Granite Rapids, those are the traditional servers, and those are 512. So now, if you have, depending on what your application is, you don't have to worry about saying, okay, I need to now, recompile it to be, it's 512, I need to recompile it to be 256, right, because I'm running it on E-core. It'll just kind of figure out that all on its own there, so you can say, okay, I've just got
So the ZMM registers are one which are kind of flexible in the length.
Yeah, the new one. Yeah, exactly.
Okay.
Right.
So, yeah, thanks so much.
Okay.